Alright guys, so in this video we're going to go through question 2b of tutorial 9 worksheet. So this is the first question. So using L'Hopital's rule, you have to prove that the f dash of a is the same as, I think I forgot to put limit sign here, so this is a limit of h goes to 0, like this, and we're going to have to prove this relationship using the L'Hopital's rule. Okay, so that's spelled L-H-O, L'Hopital's rule. So L'Hopital's rule says, sorry, there was some dust on my screen, says whenever if you have limit of x approaches a, something like that, and if the f of x over g of x, if that either approaches like 0 over 0 or infinity over infinity, you can actually so that's actually indeterminate state at the moment. So at the moment we're not able to figure out the limit of the quotient, the ratio of f of x to g of x. So remember, this is totally different from the quotient rule. Quotient rule says, what's a quotient rule? So don't mix this up with the quotient rule. So quotient rule says that if you want to differentiate f of x, some function that's made up of two functions, one on the numerator and one on the denominator, then you have to use, you guys all know the rule. I'm going to move to the right a little bit. That was f dash of x, g of x minus f of x, g dash of x over g of x squared. So, and in this case, we're just dealing with limit of f of x over g of x. So this has nothing to do with differentiation. So it says you can evaluate if you get 0 over 0 or infinity over infinity. If that occurs, then you can try this. You can just simply take differentiation of the top and differentiation of the bottom and apply the same limit and see if you get some different answer. And if you get a different answer, then that means that's the answer. Okay. I'm sorry, my cat's meowing. All right, so right, where were we? Now we're gonna prove that this is the same as the first derivative evaluated at a. All right, so if you actually apply the limit h goes to 0 here and h goes to 0 here, then you get f of a minus f of a, which is 0. And if you plug in h goes to 0 here, then you get also 0 here. So we get 0 over 0 case. Now I'm going to do a differentiation of the top and differentiation of the bottom. We go using the L'Hopital rule right there. Limit of h goes to 0. And well, I'm going to differentiate the top and bottom with respect to h. So I'm taking differentiation ddh. Okay. So yeah, you can differentiate pretty much with respect to anything. Now, what you get is f dash of a plus h, and then you have to differentiate because it's because the bracket is not just h. We got a bracket of a plus h, so we have to multiply by the differentiation of the bracket, which gives us just 1, so that's just 1, and minus, and you got f dash of a minus h, and you got to differentiate by the differentiation, multiply by the differentiation of the bracket. That's just negative 1, so that this actually becomes plus, and differentiation of this one is just 2, therefore this is 2 right there. And this becomes a limit of h approaches 0. And yep, 2, and then f dash of a plus h plus f dash of a minus h. And we can simply let h goes to 0, and this is 0, and this is 0, and therefore what do we get? We can just apply, we have applied the limit, so this is now just the f dash of a plus f dash of a, so that's 2 f dash of a, so don't worry about this thing here. Okay, I'm just going to erase that. So this is equal to over 2, so you get you get f dash of a, which is the left hand side. Okay, so some of you may think that what I did here might be a bit confusing, so I'm going to show you an example. Okay, so you can imagine maybe function of let's say f of h, let's say that's equal to h squared, and if I do f dash of h, so I'm going to differentiate with respect to h, then of course this is equal to 2h. Now if instead, using the same function right there, if I substitute in a plus h, then this would be a plus h squared. And definitely if I differentiate this one, if I differentiate this function with respect to, if I differentiate this with respect to h, then of course 2 comes out, and a plus h, and you will multiply by the differentiation of the inside. That's the chain rule, isn't it? So that's what I taught in one of my lectures. So that would be definitely just 1. Okay, so, and if you have why is it 1? Because differentiation of this one, a is just a constant and h is the variable with respect to which we're differentiating, and if you have f of a minus h, which is equal to a minus h squared, and if you differentiate that, then you just get 2a minus h, and then you have to multiply by the differentiation of the inside, and that's actually minus 1 in this case, right? Because it's negative h right there. Therefore, that's why we get a negative sign. When you differentiate this, you simply get f dash of a minus, we don't know what f of a minus h is, but we do know that when you differentiate that, it'll be just f dash of a minus h with the negative sign coming out to the front. You just multiply by negative 1, so that comes out to the front. That's why it becomes a positive value. So that's why we get this one. So so next question is, explain the meaning. It's actually the same question. Explain the meaning of this equation with the aid of a diagram. We can do that certainly. So remember how if you have some random function, we used to have a point here. We used to let that equal to x. We call that x plus h, and this was f of x, and the other one over here is f of x plus h, right? And if you take the gradient of this line, the average gradient, then that's equal to f of x plus h minus f of x over h, right? Because that one minus that one is h. And if we simply let limit of h goes to 0, then we get instantaneous gradient at that point. So this was covered in one of my lectures when Brett was away. Now we have a very similar situation, I think. So I'm just gonna copy this part. Okay, so take that. Can I copy that and paste? Let's bring it down. Okay, right here. This one is actually the same thing in a little bit different way. So I'm gonna do the, all right, stay there. Okay, oops, stay there. Okay. Right, so you got a similar function, and we're gonna call this point. So this middle point is a, but and this point here is a plus h, and I'm going to call this point a minus h. So this gap right here and this gap here is h. And we simply take the gradient between these 2 points. So this first y point is f of a minus h. And point right over here is f of a plus h. And therefore, if you simply take the gradient of this this line, the diagonal, the hypotenuse over there, then you get this one. Okay, so so it's this minus this over, and distance between this to this is 2h. And if you take limit of h goes to 0, that means this point will approach to like this point, and this point will approach this point right there, and right over there you're gonna get a instantaneous gradient, and that is f dash of a. So that is the gradient evaluated at a specific point a. Okay, yeah, right at that point there. Okay, now we're gonna move on to the next question. It says use I'm gonna go over here. Okay, I'm going to just put a line through. Okay, all good. Now next question says suppose use L'Hopital rule to prove the following similar result for the second derivative. If f is twice differentiable and the second derivative is continuous, then, so they just want us to prove that f double dash of a equals to f of a plus h minus 2f of a plus f of a minus h over h squared. So we can just do the same. Oh, actually I forgot to put the limit sign again. And you get h goes to 0. Now let's try this. So we're gonna use the L'Hopital rule again. Limit, because look, when you plug in h there, h equals 0 there, then you get f of a, and you get f of a here. So it's f of a minus 2 f of a and f of a, and everything is 0 on top. And if you plug in h goes to 0 here, 0 squared is 0, so you get 0 over 0. So that's why we can use L'Hopital rule. Otherwise, you shouldn't really use it. So we're gonna take differentiation of the top, and it's really easy now. So it's just f dash of a plus h times by 1 minus 2f. Oh, hold on. This one is just a constant. If you think about it, there is no dependence on h. Therefore, this term just disappears when you differentiate it. So I'm just going to get rid of it. My eraser is too big. All right, so that's gone. Now, if you differentiate this guy here, then you get negative of f dash of a minus h, as I explained before. And then what do you get? You get a 2h right there. Okay, now what is going to happen next is, so you can kind of see that now. So what does this look like? Okay, let's think about it. So remember how we proved over here. So I'm gonna bring this guy here again. So I'm gonna copy that and paste and bring it over here. Okay, so if you look at it carefully, so because I differentiated the top and the bottom using L'Hopital's rule, I get this expression. So I'm not going to say this is equal to anything, I'm just going to leave it like that. All right, and compare this, sorry, the one, compare this with this one. So this one is saying f dash of a is, we proved this relationship over here. So f dash of a equals to f of a plus h minus f of a minus h over 2h. Doesn't that look kind of similar to this one right here? I'm just going to get rid of that one. Okay, so we got So double derivative is simply, so if you just think about this as the new f of new f, all right, and this is another f, so it's a plus h, a plus a minus a minus h, so that pretty much just equivalent. So this is for the first derivative because this is the original function, and this is second derivative because this is the first derivative. So I think therefore we have proven that the second derivative is given by if I just draw a diagram actually, so I'm just gonna get rid of it. So you can do the same thing over here. So draw axes, and now this one is f dash of I can call this x, and you get this function, and over here is a, over here is a plus h, over here is a minus h, and yeah, I think you get my point, right? So this is a f dash of a plus h, and yeah, this one is a dash of a minus h. And because we proved the relationship with the first derivative, this just works fine for the second derivative as well. So that's done. And the second part of the second question says, what goes wrong if we don't include this term? So as you can see, when we simply use the L'Hopital's rule, so let's say this term didn't exist at the start, and we differentiate that, and we get exactly the same relationship. All right, so do we really need this term? The answer is yes. Now, the question says, what goes wrong if you don't include negative 2 f of a term? Why can't you use L'Hopital's rule then? Of course we cannot use this one, because if this term doesn't exist, does the numerator equal to 0? Just as the denominator is 0. So if you plug in h equals 0 there, 0, 0, then you get f of a plus f of a, which is 2f of a, which is not necessarily equal to 0. So therefore, you cannot use the L'Hopital's rule if this term didn't exist. Okay. Now, so in the third question, we're going to use this formula. Okay, we just proved this formula. So this formula is very useful. So what it actually helps you do is it helps you, it lets you approximate the double derivative using the original function. All right, so I'm just going to write this down again. So the formula is f double dash of a equals to, so we can get rid of the limit sign and just let it equal to approximately. So it's not exactly the same thing if limit does not exist. I mean, if the limit sign is not here. A plus h minus 2 of f of a plus f of a minus h. So, you know, sometimes you would have already experienced this when you went through some questions. Sometimes it's very difficult to get the double derivative because the original function is really complicated. So what in that case, if like an exam question asks you to approximate, so let's say in the exam they say, for example, there is a function f dash of f of x, like blah blah blah, and let's say that's really difficult to differentiate, okay, and you don't want to differentiate it twice, let alone you don't want to even differentiate once, let alone twice. Then if the question say approximate the second derivative evaluated at, for example, like 2, okay, then all you have to do is just use this formula. So f of 2 plus h minus 2 of 2 and f of 2 minus h over h squared. Of course, you need to know you can choose your h, so you can actually try, maybe if you know how to evaluate like 2.1, so the h is 0.1, right? And minus 2 of f of 2. plus, let's say this is f is 0.1 here, so it's 1.9 over 0.1 squared. So, for example, I'm just going to pick a very easy example. Very, very easy example. So let's say a very trivial example. So let's suppose we have f of x is equal to x to the power of 3. Of course we know that the first derivative is 3x squared and the second derivative is equal to 6x. So if we actually plug in 2 there, then we get 12. So this is the value of the second derivative exactly at 2. But let's suppose that this function here is extremely difficult to differentiate. So what we can do is the second derivative evaluated at 2 is approximately equal to like f of 2.1 minus 2 of f of 2 plus f of 1.9 over 0.1 square. So that's equal to 2.1 to the power of 3 minus 2 times by 2 to the power of 3. Of course, that's 8, and then plus 1.9 to the power of 3, and then 0.1 square. So let's actually calculate this one. So I'm going to bring up the calculator and we type 1. Okay, so there's a menu right there. Okay, 1.9 to the power of 3. That's equal to 6.859. So that's minus 2 times 8. So that's a 2 times 8 plus 1.9 to the power of 3. Press enter. Divide that by 0.1 squared. So did I do it right? Actually, no. I did it wrong. Sorry. So that's a 2.1 to the power of 3 minus, so that's a 2 times 2 to the power of 3, that's equal to 16, and then plus 1.9 to the power of 3. So that's a 0.12 divided by 0.1 to the power of 2. So that's equal to, exactly 12. So that's equal to 12. So I was able to get the value. So I think it's a coincidence in this case that we get exactly 12, all right? But I was able to approximate the derivative at 2 without differentiating, okay? So that's how you do it. So the question that we have is saying, okay, let's move a little bit. So all this is saying is that approximate the f double dash of a if f of a equals to 3, f of a minus a plus, right, a plus h plus 0.1 equals to 3.10, f of a minus 0.1 equals to 2.92. So all you have to do is plug this into, so it's 2 times 3 in the middle plus, so this guy goes over here, 2.92, and then this is a minus here, and this is a 3, so it's 3 there. Oh, no, this one, 3.1 goes over there, and then it's 0.1 square. Okay, so that's how you do it, I think. Let's just double check with this formula. So yeah, it's so if you look at it, it's f of so the plus one, and then the neutral one, and then negative 1. That's right. Over 0.1 square. Yeah, that's right. So that's how you approximate this. We don't even know what a is, but so you don't have to know. What it says is that just approximate f double dash of a. And that's just given by this one. And you don't have to know what a is. Okay. Right.